we've got a pattern of numbers here, 2, 4, 6, 8, 10, 12, and so on. There are various different ways we could describe that list of numbers. We could have, nice and simple, straightforward, that it is a sequence of numbers starting at 2, going up in 2s, 2 to 4, and then 4 to 6, and then 6 to 8, and so on. So it's just a sequence of numbers. A sequence just being a fancy word for a pattern or a list. Sequence of numbers starting at 2, going up in 2s. Now there are other things we can say about this as well. We might recognise this particular sequence of numbers, 2, 4, 6, 8, 10, 12. We may say, oh, they are the answers for the 2 times table. Well, that makes sense, given that the 2 times table starts at one lot of 2 is 2, and will go up in 2s each time, because each time we go to the next question, 2 2s, 3 2s, 4 2s, and so on, we're adding an extra lot of 2, so we're going up in 2s. But it is indeed the 2 times table. We might think back and we might say, oh, actually, I recognise that as something else. We can give a special name to this. It is the 2 times table, and it is, by definition, a sequence starting at 2 going up in 2s, but this is also the start of the list of what we call even numbers. And the even numbers, just a fancy way of describing the 2 times table. The even numbers, everything that can be cleanly split into 2, everything that will cleanly divide by 2, which surely is just the 2 times table, 2, 4, 6, 8, 10, 12, and so on. Just as a word of note, the numbers that go in between, that's 1, 3, 5, 7, 9, 11, and so on, they are the odd numbers. And the definition of an odd number, really, is that it's not even. So the even numbers, anything that will divide cleanly by 2, anything that we can cut in half, i.e. the 2 times table, and the odd numbers, everything else. There's one more word we can apply to this list. We can also use a bit of a mathsy word with this. And we can say that this is a list of the multiples of 2, or at the very least the first 6 multiples of 2. 2, 4, 6, 8, 10, 12. Now multiples is a word we're going to focus on, but all a multiple really is the answers to the times tables. It's just a fancy way of describing that. Playing on the same kind of route as multiplication or multiply, which of course is a fancy word for times, but the multiples of 2 are just the answers to the 2 times table. So if the multiples are just the answers to the times tables, then the first 5 multiples of 3 would be the first 5 answers to the 3 times table. So that would be 3, 6, 9, 12, and 15. The first 5 multiples of 4 would be the first 5 answers to the 4 times table. So that's 4, 8, 12, 16, and 20. And the first 5 multiples of 10 will be the first 5 answers to the 10 times table. So that's 10, 20, 30, 40, and 50. And generally speaking, a question on multiples could be this simple. It would be something like, for a mark or two, write down the first 5 multiples of, and then a particular number. The only thing that's really worth saying on that is that if you are asked to write down 5 multiples, you write down 5 multiples. Don't write 6, don't write 4, because you've not answered the question. And the first number, as in the number itself, counts as the first multiple. The first multiple of 3 is 3, the first multiple of 4 is 4, and the first multiple of 10 is 10. That number counts as the first multiple and needs to go in the list. Now, sticking with this times table idea for a minute, think about which times table questions we could do to get the answer 12. So pairs of numbers that we can times together, multiply together to reach 12. Well, we could either do 1 times 12 or 12 times 1. They're both the same thing, but we could use this kind of 1 times 12 and 12 times 1 idea. We could also do, instead, 2 times 6, or in fact, 6 times 2. Remembering again that times questions can be done in either order, in either direction, it doesn't matter. 2 6s and 6 2s are exactly the same. And we've got one more that we can use. We've got 3 times 4, and in fact, 4 times 3, the reverse. They are the only ways of making 12. Now what we can do is we can pull the numbers out of this set and we can make a list of the numbers that we've used. And the list of the numbers, well, we've used 1. 1 is a possible number that we can use. We could use 2 and 3 and 4 turns up and 6 turns up and 12 turns up. And notice I've only written them down once. I've just written down the individual distinct numbers that have turned up in these questions. 1, 2, 3, 4, 6 and 12 as a list. And what I've done in writing that list down is I have written down all of the things that 12 will divide by. I've not written down the individual questions, but I've written down what 12 will divide by. If we wanted to link these numbers up to make questions, then we'd notice that there is a pair there of 3 and 4. They are a pair because we've got 3 times 4 and 4 times 3. They are a linked pair. There's a linked pair with the 2 and the 6, and there's a linked pair with the 1 and the 12. If we wanted to make that observation. Whether we wanted to or not though, what I've got is I've got a list of 6 numbers. Now these 6 numbers again are all of the things that 12 will divide by. Each of these numbers can be used to make 12 and 12 will divide by each of these. And what I've done is I've written down a list of what's called the factors of 12. These are the 6 factors of 12. And all a factor is, well, there's a couple of different ways you can think about it. You could think about a factor being something that a number will divide by. So the factors of 12 are the things that 12 will divide by. Or you could think of it as being the questions, the times tables that you can do to make the number. So the factors of 12, which numbers can you times together to make 12? And you might need to be able to find a list of factors for any particular number. Now 12 is not that big a number and it's not that difficult a number either, but 12 has 6 factors. Generally speaking, the bigger the number, the more factors you might expect it to have. If a number is bigger, there are more things for it to possibly divide by, so there's more things that it probably will divide by. It was fairly easy to write down the questions we could do for 12. It was easy enough to generate this list because there weren't that many of them. But imagine there were twice as many or 3 times as many or 4 times as many sums that you could do. When you're asked to write down a list of factors, it's important that you get them all there. The idea of pairing them up does help, but it's still easy to miss them. So maybe we need a better way of doing this, a better way of listing factors than just this kind of slapdash approach. So we're going to have another look at the 12. We're going to generate the same list in a slightly different way. So again, a fairly straightforward question. Write down all the factors of 12. And what we're going to do is we're going to generate exactly the same list that we've just seen, but in a slightly more organised way. And what we're going to do is we're going to start with the extreme cases. We're going to think of the smallest and largest pair of factors that we can use to make 12. Well, the smallest factor of any number will always be 1. And the largest factor of any number will always be the number itself, because in the most extreme case, to find 12, we can do 1 times 12. So I'm going to put 1 at the start of my list and 12 at the end of the list. And this idea of 1 at the start and the number itself at the end will always work for a list of factors. The smallest factor will always be 1, the largest factor will always be the number itself because they are a pair. You might find it helpful to actually pair these up, like we did before, with some lines. That is personal preference. If you find that the lines underneath this list are more confusing than it's worth, don't bother putting them on. I'm going to, just to make the point about them coming in pairs, but you don't necessarily have to. That is purely personal preference. Now, why have we started with the smallest and the largest? Well, because if this is the smallest factor and this is the largest factor, then any other factors must be between these two numbers. Now, that makes sense, because a number bigger than 12 can't be used to make 12 in a times table, unless we allow for decimals. The thing is, though, with factors, we can't. Factors have to be whole numbers. We are just sticking with whole numbers here. So any other factor must be between 1 and 12, and we've bounded our list. So we're going to go down to the 1. We're going to go to the next number up, and we're going to test to see whether it's a factor. The next number up is 2. If 2 turns out to be a factor of 12, we put it on the list. If it doesn't, we move on to the next one. We move on to 3, and we test 3. So let's test 2. 2, 4, 6, 8, 10, 12. We can count up in 2s, we can reach 12. So 2 is a factor. And how many 2s make 12? 2, 4, 6, 8, 10, 12, 6. So 2 can go on the list as the next one up, but so can 6. Because they are a pair. But this is the clever bit, because now any other factors have to be between not 1 and 12 anymore, but 2 and 6. They have to fall in this bit. There cannot be a factor between 6 and 12, because 2 6s make 12 and 1 12 makes 12. Anything in here, if there was something, would have to multiply with something between 1 and 2. And the only thing that's between 1 and 2 is decimals, which we cannot have because factors have to be whole numbers. So now the list is bounded between 2 and 6. So we're going to head down to this left-hand small side of the list again, and we're going to check the next number up. So we've checked 1, we've checked 2, we'll check 3 now. 3, 6, 9, 12. We've hit 12. 3 is a factor. And how many 3s? 3, 6, 9, 12. That's 4. So 3 and 4 are a pair of factors. They can go on the list. And now any factors must be bounded between 3 and 4. And look at that. 3 and 4 are right next to each other. There are no whole numbers between 3 and 4, so there can't possibly be any factors. And this must be a complete list. Write down all the factors of 40. So we're going to do the same thing again. We're going to generate a list of all the factors, all the pairs of numbers we can times together to make 40, and we're going to do it working from both ends of the list in towards the middle. So we're going to put our extreme examples down first. We're going to bound the list. The smallest factor possible is 1, and the largest factor possible is 40, because they are the extremes. 1 times 40 is 40. We can pair those up if we like with the line. Again, personal preference whether you do or not. I'm going to. If you want to miss it off, that's absolutely fine. So 1 and 40, and any other factors of 40 must be contained within that gap between 1 and 40. So we head down to the 1, and we check the next number up. And the next number up is 2. So we check 2. Is 2 a factor of 40? If we counted up in 2s, would we get to 40? Well, yes, we would. So 2 can go on the list. And how many 2s are there in 40? There are 20. So 20 can go on the list at the other end. And they are a pair. 2 and 20 are a factor pair. And now any other factors must be between 2 and 20. Because if there were a factor in here, it would have to pair it with something in here, and there are no whole numbers between 1 and 2. So we're narrowing the gap each time we add a pair on. So 1 and 2 are already on our list. We check the next number up. The next number up is 3. If we can count up in 3s and hit 40, then we will have a factor, and it can go on the list. If we can't get to 40, then it can't go on the list. Well, we could skip a little bit. If we're thinking about our 3 times table, we'd hit 30, because 10 3s are 30, so that would be 33, 36, 39, 42. Right, not 40. So 3 can't go on the list. We get to 39, we get to 42, but not 40. So we can't put 3 on. That's okay. We'll just skip over 3, and we'll do the next one up. We'll do 4. Is 4 a factor of 40? Can we count up in 4s and get to 40? Well, yes, we can. Of course we can. Because 4, and how many 4s make 40? 10. And now we've narrowed the gap again, because now any other factors must be between 4 and 10. If there was a factor in here, it would have to multiply with something between 2 and 4. Well, the only whole number between 2 and 4 was 3, and 3 wasn't a factor. So now any other factors must be contained within 4 and 10. So we check the next number up, and the next number up is 5. 5, 10, 15, 20, 25, 30, 35, 40. Yes. 5 can go on the list, and how many 5s? 8. So 5 and 8 can go on the list. Now we've still got a bit of stuff in the middle. Any factors now must be contained between 5 and 8. We can check the next number up, we can check 6. Well, 6, 12, 18, 24, 30, 36, 42. Not 40 though, so we can't put 6 on. We could check 7 though. 7's the next number up. Well, 7, 14, 21, 28, 35, 42, not 40 again. So 7 can't go on the list. And the next number up is 8, which is already there. So this must be a complete list of factors. These two haven't met in the middle, like they did with the 12, but we have got to a point where there are no more factors contained in that gap, which means this must be a complete list. So all the factors are 40, 1, 2, 4, 5, 8, 10, 20 and 40. Write down all the factors of 48. So once again, we're going to bound our list. We're going to start with the smallest factor and the largest factor, 1 and 48. If we want to put the connecting line in to show that they are a pair, we can, but that again is personal preference. We're going to move up from 1. We're going to check the next number up, which is 2. Well, 48 would be in the 2 times table. So we can do that. Nice easy way to check that. 48 ends in an 8. 8 is an even number. Any number that ends in an even number is itself even. If you were to look through the 2 times table, you would see that anything in the 2 times table will end in a 2, a 4, a 6, an 8, or a 0, i.e. a 10. So anything ending in an even number is an even number, which means this 48 must be an even number, and if it's an even number, it must divide by 2. So we can have 2, and we would have 24. So there are 24 2s in 48, and again, they are a pair. We have to check the next number up. The next number up from 2 is 3. Well, we don't necessarily have to start counting at 0. We could start counting from something we know. We know that 30 is a multiple of 3. We could start counting from 30. So 33, 36, 39, 42, 45, 48. So actually, much as it might not look like it, 48 will divide by 3. 3 is a factor of 48. We have the 10 plus another 6 gives us 16. So 3 and 16 are a pair. And we can join those with the line. So now any factors must be contained within 3 and 16 in that gap in the middle. And we're narrowing the gap every time we add another pair of factors. We could try 4. Well, 4 is going to work. 40, 44, 48. So 4 and 12 are a pair. We could check 5. Well, anything in the 5 times table would end in a 5 or a 0, and 48 doesn't. But 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. We've skipped past 48. 48 can't be a multiple of 5, so 5 can't be a factor of 48. We can't put 5 on. 6 though, we can put 6 on, because we might know from our times tables, for example, that 6 eighths are 48. So now any factors must be contained within that gap, 6 to 8. The only thing in between there is 7, and if we went through the 7 times table, we'd hit 49, but we wouldn't hit 48, so that must be a complete list of factors. Write down all the factors of 16. So once again, 1 and 16, the two ends of our list, the extreme cases, and any factors of 16 must be bounded between 1 and 16. We can check the next number up from 1, which is 2. 2, 4, 6, 8, 10, 12, 14, 16, yes it will. So 2 can go on, and 8 2s make 16. So 2 and 8 are a pair, and now any other factors must be contained between 2 and 8. Well, we can check 3. 3, 6, 9, 12, 15, 18. Okay, not 16, so not 3. 4, 8, 12, 16. Good, right, so 4 can go on. And how many? Well, 4. And maybe something looks a bit weird about that. We've done our factors in pairs there, but we've got 2 4s on this list. Why? Well, simply because 4 4s are 16, that's true. All that's weird here is that this is a repeated factor. Don't worry about it, don't let it faze you. If you prefer to put the 4 on this list twice, because you like the idea of factors coming in pairs, and you just have that repeated number in the list, fine. If that looks really weird, and you just want to put the 4 on the list once, then just put the 4 on the list once. It's purely personal preference. It is still a pair, it's just that the pair is a repeated number. This will be true of some numbers, and we will see in a couple of lessons' time why that is. But some numbers will have a repeated factor in the middle. Again, it's personal preference whether you put it on the list twice because you like the idea of factors coming in pairs, or whether you just put it on the list once because it only needs to go on the list once because it's just a list of numbers. Write down all the factors of 2, 3 and 11. Well, we can do the same thing again. We'll start with 2, so we can have the extreme cases, 1 and 2 at either end of that list, and then any factors must be between that pair 1 and 2. Well, there aren't any whole numbers between 1 and 2. So in fact, that must be the complete list. Just 1 and 2. But that's fair enough. It's only got 2 factors, but 2 is quite a small number, so that sort of seems fair enough. It seems reasonable. Okay, we'll do 3 then. So 3, the extreme case, 1 and 3 either ends of the list. Fair enough, and they're a pair. We can check the next number up from 1, because any other factor must be bounded between 1 and 3. We check the next number up from 1, and that's 2. Is 2 a factor of 3? Well, 2, 4, no, it can't be. So that must be a complete list as well, just the 1 and the 3. But again, 3 is quite a small number, so fair enough. 11 though, well, we've got 1 and 11, and they are a pair. Well, let's check the next number up from 1. Any factor of 11 must be contained between 1 and 11. So let's check the next number up from 1. 2. 2, 4, 6, 8, 10, 12. No. Okay. 3, 6, 9, 12. No. 4, 8, 12. No. 5, 10, 15. No. 6, and then 12. No. 7, and then 14. No. 8, and then 16. No. 9, and then 18. No. 10, and 20. No. And 11 is already there. So actually, this is also a complete list. But this might look a bit more odd, because 12, we saw, had 6 factors, and 11, just one less than 12, only has 2, and has more in common with these much smaller numbers, 2 and 3. Now, in fact, these 3 numbers, 2, 3 and 11, are all examples of another type of number. And this is a type of number that you will probably heard of. Now, in fact, 2 and 3 and 11 are all examples of a type of number, a name, a property that we can apply to certain numbers. Now, this is something you've probably heard of, and there's probably a dim and distant recollection of these somewhere in your minds. Now, the definition for this type of number has 2 parts to it, and probably if you're going to recognise this word, you will remember one of the parts, and it's the one that everybody remembers if this is stuck. But everybody always forgets the other part of the definition. A number is a prime number if it has exactly 2 different factors, and if those 2 different factors are 1 and the number itself. So 2 parts to the definition. It has to have exactly 2 factors, not 1, not 3. Those 2 factors have to be different, and in fact they have to be 1 and the number itself. So bearing in mind that definition, an important question, the first of this year's big questions. Is 1 a prime number? So think about that definition. Both parts have to be true. And answer this question for yourself. Is 1 a prime number? Chosen your answer? Okay, let's have a look then. So to test for something being prime, we have to test both parts of that definition. So we have to check that 1 has factors that meet these two properties. So let's think about the factors of 1. Well, the factors of 1, we've got the smallest factor and the largest factor, which, they're the same. So certainly 1 has factors 1 in itself. But does 1 have 2 different factors? Exactly 2 different factors? Well, no, it doesn't, because they are the same factor. So the only factor of 1 is 1. We can write it as many times as we like, but they're not different. So the factors of 1 are just the number 1, which means 1 is not prime. By definition, it does not fulfill both parts of the definition, so 1 is not a prime number. Nice little 1-mark question here. Is 27 a prime number? You must give a reason for your answer. Well, it's much easier to prove that something is not a prime number than to prove that it is. Generally speaking, with these questions, the answer is more often than not going to be no. No, it is not a prime number, because it's very easy to prove that something isn't a prime number. To be a prime number, it has to have exactly 2 factors that are different, and those factors have to be 1 and the number itself. So all we need to do is prove that 27 has got factors other than 1 and the number itself. So we could say, no, something like this. 3 times 9 is 27, therefore not prime. Done. We've shown that it has factors other than 1 and 27. We've shown that it has the factors 3 and 9. Other things you could do to prove this, you could list the factors. If you actually just listed the factors of 27, you would show then that it has factors other than 1 and 27. Either way though, 1 mark, you have to have the no and you have to have your reason, and that is a reason. When it says give a reason for your answer, you don't necessarily have to write tons of stuff. It doesn't need to be a big long explanation. The maths does the explaining for you. Now there are lots of ways to generate lists of prime numbers, and so that we can generate a list that we could start to use going forwards, we're not going to list all of the prime numbers. There are an infinitely large number of them. There are infinitely many. The prime numbers do not end. But we're going to generate a list of prime numbers, and we're going to narrow it down to a list of ones that it's worth recognising, and see if we notice anything about those at the end of it. So as a little bonus, we'll have a look at one of these methods of generating prime numbers. This is called the sieve of Eratosthenes. So we've got a number grid that runs from 1 to 100, and what we're going to do is we're going to use the times tables to help us generate a list of prime numbers. So again, this is called the sieve of Eratosthenes. Eratosthenes was a Greek mathematician, and you'll see shortly why it's called a sieve. What we're going to do is we're going to use our knowledge of prime numbers and our knowledge of times tables to pull out the prime numbers. So we're going to start with the first number in the grid, which is the number 1. Now we've just shown that 1 by definition is not a prime number, so I'm going to cross it off. It's not a prime number, so we're going to get rid of it, and there it goes. Now I'm going to look at the next number up, 2. Now we have actually seen already that 2 is a prime number, but also 2 is the start of a times table. It's the start of a 2 times table. So I'm going to say we're going to keep 2. We're going to circle it. Now think about the 2 times table. So that's 4 and 6 and 8 and 10 and 12 and 14 and 16 and 18 and 20 and so on. Everything else in the 2 times table is 2 times something. That means that everything else in the 2 times table has at least 2 as a factor. To be the 2 times table, it's all the things that will divide by 2. So everything else in the 2 times table has 2 as a factor, and if it has 2 as a factor, it can't be prime. Prime numbers, remember, 1 and the number itself. We've already kept the 2. We've dealt with the case where it's 1 and the number itself. Everything else in the 2 times table has 2 as a factor and can't be prime. So it can go. So we can get rid of 4 and 6 and 8 and 10 and 12 and 14 and 16 and 18 and 20, and then the whole of the rest of the 2 times table. And suddenly, the list of possible prime numbers, which starts with 2, because we know 2 is prime, all of these other things could be prime, but they might not be. But the ones in blue cannot be prime, and we've got rid of half the possible numbers. So we're sort of sieving out the prime numbers. We're putting everything in, and we're shaking it, and some of them are dropping through as primes, and some of them are not. And all of those ones in blue have got stuck in the sieve and aren't prime and can't fall through. We're going to look at the next number up, 3. Now again, we've seen that 3 is a prime number because we tested that one out before. It just has factors 1 and 3. So we can circle 3. We can keep it. But 3 is the start of a times table. It's the start of the 3 times table. Anything else in the 3 times table will have 3 as a factor, because anything else in the 3 times table is 3 times something. So the whole of the rest of the 3 times table has 3 as a factor, can't be prime, and we can get rid of it. So the next thing up in the 3 times table is 6. Well, 6 has already gone. Then 9, so 9 can go. And then 12, which is already gone. And then 15 can go. And then 18 is already gone. And then 21 can go. And then 24 is already gone. 27 can go. And 30 is already gone. And we can keep going through in that way, and we can get rid of the rest of the 3 times table. Some of them have already gone, but that's okay. We don't need to get rid of them twice. They've already gone, they've already gone. So now we've got rid of everything that's in the 2 times table and the 3 times table except 2 and 3. Next number up from 3 is 4, but 4's already gone. We can ignore it. Next number up from 4, though, is 5. We can keep 5. 5 is the start of a times table. And in fact, the only way that we can make 5 is 1 times 5. It's the start of a times table, so that's okay. So we can keep 5. But then anything else in the 5 times table must be a multiple of 5. And if it's a multiple of 5, then it has 5 as a factor, because it will divide by 5. So 10 can go, but it's already gone. 15's already gone. 20's already gone. 25 can go. 30's already gone. 35 can go. 40, 45, 50, 55 can go. 60, 65 can go. 70, 75, 80, 85 can go. 90, 95 can go. We've now got rid of the 2, the 3, and the 5 times tables, and we've kept 2, 3, and 5 as prime numbers. Next number up is 6, has already gone. Next number up, 7. We can keep the 7. It's the start of a times table. 1 times 7 is the only way of making 7. The rest of the 7 times table can go. So 14, 21, 28, 35, 42, 49 can go. 56, 63, 70, 77 can go. 84, 91 can go, and 98. 11, next number uncoloured. 8, 9 and 10 have already gone, but we can look at the 11. We can keep 11, 1 times 11, that's fine. We checked 11 before as well. So 11 is prime, we can circle it. 22, 33, 44, 55, 66, 77, 88, 99 for the 11 times table. They all divide by 11. They all have 11 as a factor. They can go, but they've already gone. 13, we can keep. 26, 39, 52, 65, 78, 91. They've already gone. 17 we can keep. 34, 51, 68, 85, 102. That's too big. Okay. 19 we can keep. 38 already gone. 57 already gone. 76 has already gone. 95 has already gone, and the next one would be too big.
We're getting bigger and bigger gaps now. 23, 46 has already gone. 69 has already gone. 92 has already gone. 29, 58's gone. 87 has gone. Next one will be too big. 31, 62, gone. 93, gone. 37, 74, and the next one will be too big. 41, 82 has gone. Next Next will be too big. 43, 86 will be next, and that's gone. Next will be too big. 47, 94 has gone, and next will be too big.
53, and in fact the next one, 106, will be too big. And the same is true of all the others afterwards. All the ones remaining on this grid must be prime numbers. So if we write these out as a list, the list of prime numbers, less than 100, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and so on. We're just going to focus on these ones we've written out, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, because they are the list of prime numbers that are less than 30. That's enough for us to bear in mind. These are the ones might turn up, but if you're asked to write down a prime number, recognize a prime number, pick a prime number out of a list or something, it will probably be one of these. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Other things to notice about prime numbers, they do seem to spread out more. The gaps between prime numbers, they're quite closely clustered at the start, but they are much more spread out seemingly later on. Well, that makes sense, because the bigger a number is, the more things it could have as factors. The bigger it is, the more potential factors it has, so generally speaking, the less likely it is to be prime. There are still prime numbers, and again, prime numbers go on forever. But what we've done with this sieve of Eratosthenes is we've generated, first of all, the list of all the prime numbers less than 100, and then we've narrowed that down to a more usable list of all the prime numbers less than 30.